Hi. Ah, okay, thanks. Okay, so I'm going to get started. The only announcement for today is that exam regrades are due noon on Friday, so make sure you get that to me either in person or to my mailbox by then. And then I will go through the stack over break and post updates. Okay, any questions about that? Yeah.
I have two questions.
This Sunday, yes, but the Sunday at the end of break, no. So you guys get a week off of a break. So. Yeah, so the quiz after break is going to cover everything up through this Friday's lecture, which will probably be a little bit into chapter 21, but I don't know where the cutoff will be just yet. So, all right, good question, thanks. Okay, so where we left off last time was partway through chapter 20. We're looking at carboxylic acids. And I sort of covered a few different ways to make carboxylic acids that are all either ones that we've seen before in other chapters or similar to ones that we've seen before. But the last two that I covered, we sort of won't get into the mechanisms for until chapter 21. So I'm just sort of putting them up there so we have them for comparison. What I'm going to get into today is the general idea of mechanisms for chapters 20 and 21. A lot of the things in this pair of chapters are actually very similar mechanisms to each other. So you could describe them as acyl substitution. So overall, what we're going to be doing to get back and forth between one carboxylic acid derivative and another, or the acid itself, is something along the lines of, we've got a carbonyl, we've got one leaving group on here, and we're going to bring in some nucleophile, kick up onto the carbonyl, and then when the carbonyl kicks back down, we're going to boot out one of the two groups. So we get our carbonyl back, but we've replaced what the leaving group is next to it. Okay, so the exact details are going to vary, like maybe you stick a proton on first, maybe you stick a proton on here so it becomes OH, maybe Y is neutral, maybe it's negative charged. So there's some flexibility in terms of charge on this, but the main key points of the mechanism are what's happening here. Attack first, bump up to a single bond O, and then later on come down, reform the carbonyl and kick something out. So as long as you're keeping an eye out for that trend, you can sort of sort out the protonation states just based on what is going on in the environment and get something that looks like a reasonable mechanism without really having to memorize any of the individual mechanisms in this chapter, or the next one really. Okay, so questions about that kind of general theme for the next little bit here? Okay, so the first thing that we're going to see in this category, since this chapter is all about carboxylic acids, we're going to look at some things you can do with carboxylic acids. And by far the biggest deal, I guess, in this chapter is making esters from acids. So this is called Fischer Esterification. And this is the traditional way of converting an acid to an ester. Okay, so let me put up the overall reaction here, and then we can go through the mechanism. Okay, so you start with a carboxylic acid, and you end with an ester. And all you need to do this is an alcohol that looks like the ester part that you're sticking on here. So whatever R prime you want to have there. And then heat and acid. So you could write H plus on the arrow, or you could explicitly write something like H2SO4. Doesn't matter too much. Okay. So the mechanism for this one, since we're an acid, that's going to kind of dictate how things start. So this part is going to be kind of similar to the difference between acid and base catalyzed mechanisms when we're looking at aldehydes and carbonyls. If you're an acid, protonate first. That makes the carbonyl more electrophilic. Okay. So when we start this, the carbonyl is going to go get an H plus from wherever. And now that it's more attackable, more electrophilic, the other thing that we have around, this ROH, or R prime OH, even though it's not a great nucleophile, that can come in and attack the carbonyl. Kick that up. And that gets you to here. Okay, so this is, I don't know if I use the phrase up here, but this is the tetrahedral intermediate. Let me actually write that down up here as well. Okay, so that's kind of the key step during any of these reactions in these chapters is you go through a tetrahedral intermediate where the carbon of the carbonyl is sp3 hybridized for a while. Okay, so we've just reached that point in this mechanism. Now we just need to set things up so that we can come back down and boot out our leaving group. But we got to do a couple other things first. One is this group that we just attacked with, we got to get it to neutral, so we need to lose a proton off of here. And if we want to boot out our leaving group, I guess the equivalent of X in this general mechanism up here, it's going to be a lot easier if we protonate it first to turn it into a good leaving group. And since we're in acidic conditions, that seems a lot more likely since we have extra protons. So here we got to add an H plus onto it. So this is looking a little bit similar to, say, acetal formation before, where we need to lose an H and add an H. We can actually show those as two separate steps, which I think is how I did it in the notes. Or you can just show it as sort of one concerted intramolecular proton transfer. Is totally fine too. So just have that, the group that needs the proton picks it up from the group that needs to get rid of a proton. And that gets you to here. And now we can go ahead and finish up this like skeleton of a mechanism that I drew up here. Have the carbonyl oxygen kick back down, boot out our leaving group. And we're almost done. We just got to get rid of that extra proton at the end to get back to having a neutral carbonyl. So then you can deprotonate it. If you want, you can show details, but you don't have to. And that gets you to here. Okay. So questions about that one? Okay, so one important thing to mention is that kind of like I showed up here where X stays as its own group and Y stays as its own group, and maybe there's some proton transfer going on, but it's still like one individual piece. The same thing down here, like the ROH all stays together except for the proton during the whole mechanism. So when we're done, when we've made the ester, this oxygen here, I'm going to draw a little asterisk on it, is the oxygen that came in with ROH from the start. So it's this oxygen here. So people have actually proven this by doing isotope labeling studies. They get like some special isotope of oxygen, bring it in as part of the alcohol, and it gets incorporated as the OR prime group of the ester. So that's kind of how we know that's going on. Okay. So questions about that? Okay, cool. So Fischer esterification is kind of like the old school default way of making esters. It's pretty widely applicable. There's some downsides. One is that you're losing a molecule of water as you do this. I don't think I described this in the notes, but just as a heads up here. So it's losing a molecule of water, so like a lot of other reactions we see that kick out a molecule of water, if you have a lot of water around, Le Chatelier's principle is not going to be working in your side, and so if you really want to help this reaction, you can use 4 angstrom molecular sieves to get the water out of there, or I guess use concentrated acid will also help, or just make sure you have a ton of alcohol around. Like a lot of the time you'll just use alcohol, whatever this one is, as the solvent, and then just throw in a little bit of carboxylic acid, and that favors the product. But if you do this in a bunch of water, it's just going to revert to the carboxylic acid. So the less water you have, the better if you want to drive the forward reaction. Okay. So if you do start with an ester and you have it around a bunch of water and acid, you're actually going to be doing the opposite reaction, ester hydrolysis, which we'll look at in the next chapter. Okay, so questions about that? Yeah? Mm-hmm. Yeah, that's 4 angstrom molecular, or I guess that's one option. Yeah, the another option is like the drying agent that we have in lab. Yeah, that has some pluses and minuses. Usually, like if you're doing an actual reaction with an acid catalyst, mol sieves are kind of safer because the drying agent might potentially, break down an acid. But yeah, there's a ton of options in that family of like things that soak up water and hopefully don't do much else. So, yeah. Okay. So this is kind of one option that we have where the alcohol oxygen is the one that gets incorporated into the ester. We actually see a couple of other options that don't do that. So other less generalized options. Both of these boil down to do SN2 on something with a carboxylate. So in this case, the oxygen that ends up part of the OR group is actually going to be the one that started with the acid instead of the one that started with the alcohol. Okay, so we're going to look at 2 different versions of this. One of them looks really weird like a setup for SN2, but it turns out it actually works okay once you start going through the mechanism for it. Okay, so diazomethane, which is CH2N2. What that looks like is actually this thing. It's a CH2 group with a negative charge, and then oh boy, that group is going to fall off real fast if you try doing anything onto it because it's going to produce an N triple bond N, which we know is very favorable as a leaving group in a reaction because it just wants to go away and be nitrogen gas by itself. Okay, so the way this gets started is okay, so really you want to look at this in 2 parts. One is we've got something that's almost a methyl group attached to a really good leaving group, but we don't actually have a methyl group that's SN2 capable yet. So the first thing we're going to do is get it to a full CH3 methyl group by ripping a proton off of the carboxylic acid. So like this. And now we've got something that's very SN2able, and we've got a carboxylate here, so this is just going to do SN2 at this point. Okay, so that's great for making methyl esters, just because diazomethane is actually not too difficult to make in the lab. If you actually have a special piece of glassware, a special setup called a diazomethane generator that you can buy, and that churns out this stuff, and then you just immediately pump that gas into your carboxylic acid solution, and you make the methyl ester out of it. It's not too versatile for other options, just because other diazomethanes are harder to make and trickier to work with. But if all you want is a methyl ester, then this is perfect. This is super easy to work with, assuming you have the piece of equipment that you need. So I haven't covered naming esters just yet. We'll get to that in the next chapter, but it's an ester with a methyl group as the OR group, so that's kind of the term to describe it, is a methyl ester. Okay, so questions about that one? Okay, cool. So a similar option is a lot more along the lines of what we're used to seeing for SN2. So just a carboxylate, like the actual minus charged oxygen plus whatever alkyl halide, but turns out carboxylates are weak base poor nucleophiles, so we have to be careful with our alkyl halide that we're not getting into like E1, SN1 territory. Okay, so like again, methyl's probably the best choice, or benzyl is another good choice because we know benzyl is great at SN2. So alkyl halide, and then usually you're going to make the carboxylate from acid plus like a mild base like potassium carbonate's pretty common. Okay, so that might look like you start with the carboxylic acid, it gets deprotonated by, all right, so the K2CO3 we can show as like 2 copies of K plus, and then like a CO3 with a -2 charge. In the notes I have like one of the potassium split off, and then the rest I have as KCO3 minus, which I think is how they have it in the book if I remember right, so I just decided to go with that. But really you can show like one or both of them split off, but really it doesn't matter that much because all you're using it to do is deprotonate the acid. Okay, so we get the carboxylate, and now we can just go do SN2. The more of a softball we pitch this thing, the better. So like the best alkyl halide we can get for SN2 is an alkyl iodide. So like methyl iodide is probably the easiest possible SN2 substrate. And that will also get us a methyl ester in this case. So the same as we got up here. Okay. So questions about that one? Yeah.
Does it work for secondary alkyl halides or mostly primary?
So weak base poor nucleophile would be getting into E1, SN1 probably. So really, like, primary is pretty much it. You might be able to get away with like benzyl iodide, because we know this is super friendly to SN2 as well. But really, like, you're pretty limited in this. Like, anything more sterically hindered than these, and you'd probably have to default back to Fischer. And then, sorry, you had a question as well?
Is just similar. You can make things other than methyl esters.
Yeah, and I think there's probably ways to like extend both of these out a little bit, but you're still limited by, you're trying to do SN2 with a nucleophile that's just not really cut out for SN2 very well. And so, like, yeah, Fischer is kind of probably the better way to go if you're not sure. Yep. Okay, so other questions about those ones? Okay. Okay, so the way you would write these overall reactions would be either carboxylic acid, and then you can just write diazomethane, CH2N2 on the arrow. Or you can do carboxylic acid and your alkyl iodide, and traditionally a weak base, like weak inorganic base like potassium carbonate. And that'll get you the same thing. Okay, so 3 different methods of making esters. But really, if in doubt, stick with Fischer. It's pretty hard to mess up Fischer, as long as you don't have any like really acid-sensitive groups on your molecule. Okay. So a lot of this chapter is just starting with a carboxylic acid and converting it to various different acid derivatives. So we started with acid going to ester. Next up, we're going to look at converting acids to anhydrides and chlorides. Okay, so for these, we're not actually going to look at the mechanism for it. We're just going to look at the overall reactions. I'll explain why in a second, but for the chloride, we obviously need to have something with chlorine in it. Easiest option is actually something we've seen from a way back. If you remember in chapter 10, I think it was, when we took an alcohol group, used SOCl2 and converted it to a chloride. Turns out that actually works for acids too. You can convert the OH group of an acid into a chlorine, which turns it into an acid chloride if you use SOCl2. We are going to see another option, phosphorus pentachloride as well. PCl5 will do the same thing here. So that one does not work for alcohols, but it does work here. Okay. So that's pretty much the only level of detail we're getting into on that one, unfortunately. Okay, so to make the anhydride, so again, kind of like the name implies, this involves removing water very forcefully from the reaction. And so what we're going to use is a very powerful dehydrating agent, P2O5. Which you may also see written as P4O10. It turns out this thing makes this crazy like tetrahedral shaped thing with phosphorus at the 4 corners and oxygen like linking every vertex of the shape and also like one oxygen double bonded to each phosphorus. So the mechanism is kind of complicated as this whole tetrahedral thing opens up as it gets water added to it progressively. So we're not really going to get into that too much, but this is actually, like, there's tables of different dehydrating agents and like what circumstances they're most useful for. And P2O5 is definitely kind of bringing out the big guns for pulling out water. I guess this actually kind of gets back into Michelle's question of like, you know, should we use molecular sieves or should we use the drying agents like anhydrous? I think you guys have sodium sulfate in lab. But yeah, this is like way up the ladder of how strongly this thing is going to pull water out of it. Okay, so this one, again, we're not really going to draw the mechanism for it. It's pretty much all you have to do is write P2O5 and 2 copies of it are going to stick together with a molecule of water taken out. Okay, so that's kind of the default option for making anhydrides. One other option that we do actually see is kind of an interesting like anhydride exchange. Sorry, question? Or, no, okay. So turns out that if you take something like a diacid that has 2 carboxylic acids in it, and you bring it together with an anhydride that's not cyclic, you can sort of think of it as the number of water molecules is conserved. So like this whole thing is going to lose a water molecule as it cyclizes down, and this whole thing is going to gain a water molecule. And you're going to get to this thing like forming an anhydride onto itself as both the acids sort of wrap around and join together. And meanwhile, the water molecule that it releases goes and splits up this anhydride to make this. Okay. So pretty much the only reason this is favored is because this one happens to be cyclic. And so you start out with 2 molecules and you end up with 3 molecules total. And so I guess entropy-wise, this side happens to be a little bit more favored. Okay. Questions about that? Yeah? Mm-hmm. Good question. I'm actually just about to start getting into how those apply here, yeah, in the next section. Yeah. Okay, any more about anhydrizing chlorides real quick though first? Okay, cool. So, protecting groups are going to become relevant for a different reaction that we saw in the last chapter, but which we're now bringing back here, which is reductions. Okay. So what are the 2 reducing agents that we saw in chapter 19 if we wanted to go aldehyde or ketone to an alcohol? Yep. Yep. And I guess there's actually a third that doesn't show up here, which is totally different from the other 2. Involves nickel. Yeah, nickel and H2 is the other weird one. They don't actually mention that in this chapter, but I don't think it works for this reaction. So we saw NaBH4 and lithium aluminum hydride for ketones and aldehydes. And in the last chapter, we treated them as totally interchangeable. You can use one or the other, doesn't matter, so long as you set up the reaction conditions so that this one is a stepwise, like LAH first, then protic conditions. This one you can do protic conditions at the same time. So that was the only difference between them. For this chapter, now that we're looking at carboxylic acids, LAH is going to reduce acids. Sodium borohydride is not. Okay, so this is actually a pretty significant difference between them in terms of what's going to change to the molecule. Okay, so the overall reaction is going to look like carboxylic acid, and then first lithium aluminum hydride, and second H3O plus. Briefly, it's going to go through a form where it's reduced down the carbonyl. You get this diol looking thing, which we know can go to an aldehyde, and then immediately that's going to get reduced again to just a primary alcohol. All right, so lithium aluminum hydride is going to take this thing down all the way to the 1 bond to oxygen state, even though we started at 3 bonds to O. Okay. So I'm not really going to get into the mechanism for this. If you're curious, I think it's either in the book or in the solutions manual, but it's similar enough to aldehydes and ketones. Okay, so now that we have some selectivity in terms of which groups get reduced by which reducing agents, we can actually start differentiating between aldehydes and ketones in kind of a useful way. So and this actually kind of ties into the lab that you guys did last week, those of you taking lab, where we did reductions of ketones. But if you want to reduce the ketone or aldehyde, but not the acid, then what reducing agent are we going to use? Yep, sodium borohydride. So we got an aldehyde at one end and a carboxylic acid at the other. Hitting this thing with NaBH4 is only going to go for, this chalk sucks. All right, is only going to go for the aldehyde end of things. Depending on the actual circumstances, this gets kind of, yeah, I guess let me just, okay, now I have an alcohol solvent. Okay, so the aldehyde here is going to get reduced down to the oxygen, to the alcohol, but the acid over here stays unchanged. What if we want to do it the other way around, though? Because we don't have any reducing agents that'll specifically go for just the acid but not the aldehyde. But, and this is tying into the question about protecting groups, if we try to protect the carbonyls on this thing, protecting groups turn out not to work on carboxylic acids. So if we hit this thing with a protecting group, it'll only protect this end, then we can safely reduce the acid, and then we can deprotect. So here's the gist of it. Protect, LAH, deprotect is what we want to try here. Okay, so that might look like okay, so I'm sticking with cyclic acetals because that's kind of the most useful way to do it. Okay, so when we protect, only the aldehyde gets changed. Carboxylic acid stays as is. One thing that you might need to worry about as a byproduct, so we've got an alcohol here and a carboxylic acid, and we have H plus as a catalyst. That actually looks like we might be getting some Fischer esterification going on as well, because we know these are all the setup for Fischer esterification. Turns out the acetal protection happens fast enough, like Fischer is kind of slow a lot of the time, that you can sort of get away with this, but you would be getting some byproducts of the ester forming as well. Okay, so protect, then LAH. And might as well include all the details on that happening. And then deprotect. So this would involve longer reaction times or higher temperatures than what we use to finish up the LAH step. Okay, and that's how we can affect the acid without actually affecting the aldehyde at the end. Okay. Questions about that one? Yeah.
So for this, we would need to show a separate step to deprotect.
Yeah, or if you just did like H3O plus in heat, you could just skip straight to the end if you wanted to on synthesis.
Would you be concerned about having the H plus from your protectant step and following that with the LAH? Would you have to like?
Oh yeah, so you would definitely like get this thing all cleaned up and neutralized and everything in between. If you just like, you know, had this mixture all sitting around and threw in your LAH, then probably call the fire department after doing that. Yeah, because yeah, that would totally, like if the acid and the LAH got together, it would probably neutralize pretty enthusiastically. Yep.
This is reminding me of that, but what is like the general formula in
Oh,
talk about like making anhydrides?
yeah, so it's, sorry. This functional group where you've got basically two carboxylic acids sort of stuck together on either side of an oxygen, because if you, I guess if you draw out like the other acid here, basically one of them's losing an OH and one's losing an H when they get together, and so overall you're losing a molecule of water, which is kind of how they got their name. So,
Was this another way to say diester bond? Or
not really. I guess just because chemically they're pretty different from esters. So yeah, anhydrides are kind of their own thing. So esters are a lot more stable because they have a much smaller delta positive. So, yeah. Okay. Other questions about this? Okay, cool. All right, so that about does it for, I guess, converting acids to other acid derivatives for this chapter. We're going to see a whole lot of reactions going the other direction in the next chapter. But to wrap up this one, we're actually going to look at one specific reaction that's unique to carboxylic acids alone. So what we're going to look at here is a weird one called decarboxylation. And this is loss of CO2. Okay, so you've got to have special circumstances set up for this to work. So it needs a beta carbonyl. With an acid group. So some examples of what might work here are so here's our acid. alpha, beta. Here's a beta ketone. So this would be a beta keto acid for one example, or you could have like a beta ester acid. Doesn't matter too much what the second carbonyl is, it just has to be on the second carbon away from the acid group. So what's going to happen here is we're actually going to lose the entire carboxylic acid group, this CO2 unit, and the H here is basically going to end up sticking on to where the carboxylic acid used to be attached. So same thing here, the entire acid group falls off and the H just moves over to shorten up the chain. That's not what happens during the mechanism, but you can sort of think of it that way schematically in terms of predicting products. Okay. So the mechanism for this one, it really helps to keep it straight if you think of it as being kind of like Diels-Alder. You want to start by setting this up so that the OH group of the acid is actually hydrogen bonding onto the other carbonyl. Okay, so rather than drawing it like in this linear form like we got over here, really this thing has a pretty strong incentive, even when it's just like sitting around on its own, to sort of curl up and start hydrogen bonding onto itself. All right, so here's our ketone. Normally we could draw it like a keto acid like this, but really this thing is going to sort of swivel around so that its carbonyl is sticking out this way, and it's now hydrogen bonding with its H back onto its other carbonyl. Okay, so from here, this is where you're seeing a six-membered ring with one thing that's not quite a bond yet, but is about to be. This is where Diels-Alder is going to start sort of happening, or some Diels-Alder-like arrows. You know, I'm noticing in the notes that OH bond here, you really can't tell that's a dotted line. It just looks like a solid line. But yeah, this should be a dotted line. It's a hydrogen bond. It's not a real bond just yet. Okay, but when we start doing the mechanism, we're going to make it be a real bond. So we're going to show one arrow coming out of here and forming a new OH bond up here. And we're going to do the same thing we did during Diels-Alder or when we were showing resonance on benzene. We have three arrows that all click around the ring in the same direction at once. So that kicks down, and that kicks down, and boom. Where does that get us? Okay, so we now have a single carbon to oxygen bond. That oxygen now has a single bond to hydrogen. And meanwhile, we have the O over here, which now has a double O to C bond. I'll just draw the C explicitly. This will draw it here as well. Okay. Meanwhile, this carbon still has its double bond O hanging off to one side. Nothing's changed there. And then finally, we now have this C-C bond here in the bottom left that started as a single bond that has now become a double bond. Okay, so just in one click, everything's sort of changed for this molecule. It went from having a beta keto acid in this case to, what functional group is this? Yeah, that's an enol. So we're going to be seeing some more stuff that it's about to do. And then we've also just spat out a molecule of CO2. Okay, so we know the enol means that it's going to tautomerize to the keto form or the aldehyde potentially, depending on, oh no, it's got to be a ketone. And if you want, you can go show all the arrow pushing for how to get from enol to ketone. we're not explicitly using any acid or base as part of the environment, but you're starting with a carboxylic acid, so it's going to be the acid catalyzed mechanism. Okay, so questions about that one? Yeah?
So if that were instead of the beta keto acid, if it were the beta ester acid,
Mm-hmm.
you still get that ketoenol carbonization?
Yeah, so if you started with the ester out here, then it would just be like OR all along, but the enolization step still looks the same. So, good question. Okay, so overall, pretty much these molecules will just fall apart on their own as soon as you heat them up very much. So you take something that's drawn as like the beta keto acid and you heat it up, and you can just show it going straight to the product there. Okay, so in other words, these are fairly fragile molecules that'll just drop off a molecule of CO2 as soon as you start heating them up, which can be useful. As we'll see in a couple chapters from now, sometimes we deliberately want that to happen, and we're sort of saving up decarboxylation for the last step once we've taken advantage of it chemically in other ways. But sometimes it's kind of annoying because this is not going to stick around for very long as soon as you heat it up. Okay, so other questions about that one? Okay, cool. So that's the last reaction for this chapter. I don't think I can get through the synthesis problem in 3 minutes, so I think I'm going to wrap it up there for the day and then do synthesis next lecture.